So we have the components of a wave as wavelength, and then we have height here. Does anybody know what the correct term for height of a wave is? Yeah? Amplitude. So wavelength is from distance from peak to peak, and it's this little lambda sign, and we measure this in a distance unit. So it means it should be with meters or centimeters or nanometers, something with distance. Here is how we describe frequency. So you can think of frequency as like a wave in the ocean passing a buoy. So if that wave passes frequently, then it's high frequency. If it's passing less frequent, it is low frequency. Frequency and wavelength are inversely proportional. It means that as the frequency decreases, what happens to the wavelength? Increases. So you get a longer distance here. As frequency increases, wavelength decreases. So frequency is this little nu symbol, and it should have like a little hook on the end of the V, but you can just write it as a V. It is, its units here are written as 1/second. So it's basically like how many times does it pass per second. So 1/seconds. You can write that as an s to the -1, because anything raised to the -1 power means it's, just put that in the denominator. Or you can call it a hertz. And a hertz has Hz as its unit. So basically the guy who invented or came up with this, Henrik Hertz, just named it after himself. So sometimes people will just keep it at hertz instead of reciprocal seconds. And then the distance, again, in meters, nanometers. The AP exam loves to mismatch units. So don't expect them to always be the same. And then the speed of light is 3 times 10 to the 8th meters per second. They might give it to you in centimeters. It is on your equation sheet. So when you're looking to do this, I've seen it as a multiple choice question usually. It's very simple to do because it's just a quick little algebra problem. But the number, you need to make sure that you go and look at your constants on your equation sheet. All right, so let's try it. Find the frequency of green light that has a wavelength of 545 nanometers. In the next slide, I'll talk about the visible spectrum. So right now, we're just going to say, okay, green light has this specific wavelength. And then you're going to determine the frequency from the equation on the previous slide. So just a little bit of algebra, and then recognizing right away what's the trick here. What's wrong with this? Right, it's in nanometers, we need to change it to meters. So you need to remember your metric conversions, use a little dimensional analysis. I wouldn't just do it in my head. Dimensional analysis, and then plug it into the speed of light equation. All right, go ahead and try. So I'm going to show you how I would approach this problem. I would immediately recognize, and this is how you should grade or get problems graded. I write down the fundamental equation first, so I know that I need to use this. I recognize that the 545 nanometers is not going to be usable because this is in meters. So I'm just going to do a quick dimensional analysis problem. I know that it goes micro, nano, pico, and I taught you that's 10 to the 6th, 10 to the 9th, 10 to the 12th. So nano is 1 times 10 to the 9th nanometers in 1 meter. So rather than, if this were, even if it's not, if it's a free response question, I don't bother myself too much with like typing this into my calculator. I know that this is technically like 1 times 10 to the 0. So this answer is 545, just following along, 545 times 1, times 10, 0 minus 9 to the -9. This is not proper scientific notation, and if you typed it into your calculator, you would just move your decimal and then adjust your exponent. But I don't even need to waste time with it because I'm just going to be able to use this and plug it into my calculator. So this is a meter. So now I'm going to go and use the equation 3.00 times 10 to the 8th meters per second is equal to 545 times 10 to the -9th meters times frequency. So I'm solving for frequency here. So now I just have to divide through on each side. 545 times 10 to the -9th meters. And you'll notice now you have a numerator meter and a denominator meter, and they cancel out, and you're left with seconds in the denominator. Isn't that the unit for frequency? So I love to check my answers by making sure that my units are what they should be. I told you that a little bit yesterday and when we were checking our last test. When you use units, dimensional analysis, you really can make sure that your answer is correct. So on my calculator, we're all going to make sure that we get this correct. This is just a review of how to enter numbers. 3, E, 8. Then you're going to hit the divide button on your calculator. Then you're going to hit 5, 4, 5, E, -9, and then equals. Make sure that you get that answer. Okay, so the answer is 5.50 times 10 to the 14th hertz. Thumbs up if you got that. All right, most of you. So if you're not getting that, I think there's like one of two, or I didn't see. Did you get it? Okay. If it's a calculator issue, then you just need to make sure that you're recognizing how to use your own calculator. And make sure that you use the EE button and not hitting times 10 twice, essentially. You're going to multiply by an extra 10. And then you should always check your answer by doing your exponents. So 8 minus a -9 would be about 17. And then obviously, because this is a not proper scientific notation, my exponent would be adjusted slightly. But you just ballpark it. Like, oh yeah, this makes sense. I typed it in my calculator correctly, rather than it being a negative exponent or something. You can check that you didn't hit something incorrectly by looking at your exponents. All right, so here's our continuous spectrum of light. So we're in the visible light range is what our eyes can see. It falls from 400 nanometers to 750. This is Roy G. Biv. Except when we look at it in terms of the electromagnetic radiation, this is the whole spectrum of what we call light. But you have to recognize that light isn't just light that we see, that light falls from basically gamma rays all the way to radio waves, which are long waves, right? So we consider all of this light, which has energy, and we'll get to how it plays into photons and so forth. But this is our visible light range. And if you recognize, it doesn't go Roy G. Biv, right? It goes Viv G. Yor, right? So we have low wavelength, high frequency, long wavelength, low frequency. So that's the order that this goes in the visible spectrum. So if you're in the visible spectrum area and you fall out of it, you won't be able to see the light. All right, so Max Planck hypothesized that the energy radiated from a heated object, such as a stove element or a light bulb filament, is emitted in discrete units or quanta. So quanta is this word that we're going to use to describe specific amounts of energy. That's what quantum is. Quantum energy is a specific amount of energy. Quantum is a specific amount of energy. All right, so let's pretend that this is an energy example. Everything is going to have atoms, not everything. Atoms are going to have a quantum of energy required to make electrons jump. That's where we're going with this. And what that means is that there's just a threshold. So pretend that we're boxers. All right, so who's the boxer in here? Anyone want to be my pretend? I'm just going to use your name. Good job, Drew. So you can be the boxer today. All right, so Eddie and I are your opponents, right? And you need to knock us out. Are you going to require the same amount of energy? I know I look tough, but clearly Eddie's much tougher than I. So who requires more energy? Eddie does, right? So the quantum of energy required is different for he and I, just like it will be different for different electrons that are held in the atom. So that's what we're getting with this. When we, I want to use an example of this heating up of water. What we think is happening when we're heating a pot of water on the stove is we think that we have, as energy is being added, the intensity, it starts to boil. So we visually see this happening, right? We see okay, it starts to get hotter, and then we see these little air bubbles kind of coming up, and then the water begins to bubble, and then it begins to bubble more rapidly. But really what's happening, and we don't see this, is that as energy is being added, it goes up in these little quantum steps. So once it absorbs this much energy, then it jumps, and it keeps jumping and jumping. It'll either increase by a full quantum or not at all. It's like climbing the rungs of a ladder. So as you're climbing, you can't step in between a rung. There's nothing there. You either go to the next step or you don't go at all. So the quantum is what we're looking at these steps, is the height of each step is equal to 1 quantum of energy for a certain frequency electromagnetic radiation. So frequency is specifically related to that quantum of energy. So this is Planck's equation with Planck's constant. We have the specific amount of energy, the quantum of energy, in joules. So joules is a unit for energy. Just always keep that in mind, because when we get to topics like thermodynamics, that has energy. We want to make sure we're using the correct unit Energy is always in joules. Planck's constant is joules times seconds, and then what's frequency? Reciprocal seconds. So if you stick a 1 divided by seconds here, your seconds cancel, and you're left with joules. So these are related directly, which means that if frequency increases, energy increases. So we're talking about the frequency of light, right? So it's like this frequent versus this frequent. High frequency light has more energy. So like back to my boxing example, if I'm punching one of those bags and I'm hitting it, right now I'm using some energy, right? But if I go like this for the next minute, my heart rate's increasing, my fist is moving a lot faster, my frequency's increased, and then in turn what increased? Do I have to do this again? The equation? Frequency increases, so what else increases? Energy. I'm using way more energy to do this compared to this, right? So if you think about light and the frequency of that light, higher frequency light supplies higher energy. So the more energy you have, then that will determine whether or not these electrons in atoms are going to be ejected. So this ejection process comes from the photoelectric effect. So scientists made this observation, and they didn't quite know how to explain it, and so they used this sort of experiment to describe that atoms have electrons that are held in sort of orbits. So when you're kind of going through this lecture with me, all of it's going to sound sort of new to you, but you have to take it as if you were a scientist not knowing how the atom already looks. Like you already know the protons are in the center, you already know electron configuration, you already know that there's sublevels because we taught you that already. But pretend that you are new to all of this and you're figuring out what the atom looks like. So this is sort of the experimentation that they were using to determine how are atoms designed, how are the electrons held. So here's our first experiment to discuss electrons being in different energy levels. So scientists would observe a clean metal plate. This is how they set this up: a clean metal plate, a collector plate. They would attach it to a battery, and they would have a light bulb here. So a metal is made up of atoms, right? Like say I use tin. It has tin atoms, right? And the atoms have electrons. This is a collector plate. So the electrons, if they get emitted, jump to the collector plate, and then they complete the circuit, and then the lamp shines. Do you guys have any of those little toys where you have to complete a circuit at home? Not that you make a circuit. We just bought for my son this summer, and I've debated bringing this in to you guys. We bought him 2 things because they're so much fun to pull pranks on people. It's like a pretend piece of gum, and you complete the circuit. When you try to grab the gum, it shocks like the heck out of you, like my toes tingled. And then we also bought this year, which I debated bringing into school, a pen that does the same thing. So if you guys ask me to borrow the pen, you go to depress the top, and you complete the circuit, and you get a little jolt. They're all fun. I'll wait till you guys know me better till I shock you, I promise. So the idea is you complete the circuit so the light bulb turns on. All right, so what you need to look at the next few slides is you need to make observations about these little waves here. So they're going to change the numbers and the frequency of them so to make the observation. So this is light, not visible light, but more intense light, like UV light or something with a higher frequency. So we're trying to get the electrons to jump out of atoms and go to the collector plate by shining light on them. And the only way to get an electron to jump is to like smash it. Does that make sense? You're going to hit it with enough energy that it gets ejected out. So let's just remind ourselves that the atom is essentially nucleus in the center, n equals 1, 2, 3, and so forth, right? We have electrons in these different energy levels. All right, so the first fact is that when we shine highly intense, low frequency light, no electrons are ejected, even if it shines on the surface for several days. This is sort of counterintuitive. You guys know that if you put a pot of water on a stove and you turn it on really low, will it eventually boil? Oh, you're all like, oh my gosh, I don't want to say anything. It will. Guess what? The water will boil. Like, you keep it on really low for like an hour, your water will boil, right? Or if you put it on really, really hot, it'll boil faster. Make sense? But that's not what happens with this. You can't put low frequency light on the metal and eventually it'll absorb enough energy to make it jump. That doesn't happen with the electrons in an atom. It has to meet a threshold. So like to knock Eddie out, doesn't matter if you throw 15 punches at him, if they're not of high enough energy, you're not knocking them out. Make sense? So these electrons, even though I'm throwing 15 punches at this, their energy is not high enough. It's not high enough to make any electrons jump. The next one says, when the threshold frequency is reached, electrons are ejected immediately. So it doesn't matter how intense that light is, as soon as you supply enough energy, you're going to knock those electrons loose. So you hit that punch hard enough with enough energy, you've met the threshold, the electrons jump, and the lamp turns on. Third fact, increasing the intensity of the light at a frequency that will cause electrons to eject results in a higher ejection rate. However, all ejected electrons share the same velocity. So it doesn't mean that they go faster, it's just more of them get ejected. So now you're throwing a threshold, and now you're throwing 15 punches, so I can just knock out more of you. Does that make sense? I just came up with this knocking out example from boxers. I'm good like that. Just go on the fly. Fourth fact. Increasing the frequency of the light increases the velocity of the ejected electrons. However, all of them share the same velocity. So what you should notice is now I'm hitting this with a higher energy, higher frequency wave. Not as much, not as many lights, but still a higher energy. So if I hit them with higher energy, they're going to go faster. So you can think of this sort of like that boardwalk hammer thing, you know, where you throw the hammer down as high as you can and then it bing, goes to the top. So if I hit that, mine will go up halfway, and then, you know, Cole goes and hits it, it ping, all the way to the top, goes faster. Got it? So higher energy, once you've met the threshold, then if you increase the energy, then the electrons are going to go faster. Everybody got this? Sort of a fundamental experiment you need to be able to explain. So here's what the theory is. Go ahead and read all of this on your own for just a minute and kind of make sense of it. If you need to jot down some notes next to it based on what I just said, use this time. So that last statement here, the electron absorbs the photon, is sort of, now I'm throwing that into this piece here. So the electron that's in the atom acquires enough energy and it jumps, but that energy that is getting from the light is considered a photon. So the energy per photon is really what we're looking for. So each of these particles, because light is considered to behave as a wave and as a particle. That's kind of hard to envision, but it's both a wave that's traveling to you, but it's also a particle. So that particle is called a photon. Got that? Okay. Forces of attraction between the electrons and the nucleus result from opposite charges. So now we're going to discuss taking these electrons and smashing them and getting them to jump out. So now we're going to talk about the specific amount of energy and why does the energy increase for different atoms, right? Not every atom requires the same quantum of energy. So we're going to look at how electrons are held. All right, so you remember that they're held, otherwise they would just fly away because they have electrostatic force of attraction, right? A positive and a negative charge holding them together. And then it doesn't collapse on itself because they are held in shells. So here's this wonderful thing called Coulomb's law. And it's really useful when explaining free response questions. So you don't ever have to put numbers in this to calculate anything, but you're going to use it a lot because it's just easy to see and describe a free response question to discuss force of attraction. So F is force of attraction. K is a constant. We don't really care what that is. Q1 and Q2 refer to charge. So for this example, for this lecture, we're going to assume that Q1 and Q2 are charges for protons. Basically, the number of protons in an atom is going to increase the charge of that atom. But eventually we'll get to like compounds. So like calcium's a +2 charge and chlorine's a -1 charge. So that's 2 times 1 is 3. That's where we'll eventually go with this. But today we're just going to look at protons. D squared is the distance. All right, so if charge increases, what happens to force? Just use math. If I increase the numerator, what happens to force? You guys are so afraid of saying the wrong answer, aren't you? I told you. Only if you have maybe if you said red right now, I would say that's probably a horrible answer. Just come up with a random word. If you increase the numerator, what happens to force of attraction? Increases, right? Red. What happens when you increase the distance? It's going to decrease the force of attraction. All right, so here's my nucleus, here's my electron. They're close together, so force of attraction is pretty strong, like holding magnets. And then I go here, and now they're further away. Obviously, the force of attraction from here to here is decreased because distance increases. Make sense? I mean, it makes sense, but then you could always just even use the equation if you weren't quite sure. All right, so our Bohr model of the atom is the one that looks like Jimmy Neutron. So again, remember that you're going to kind of follow this lesson as if you didn't know that there were sublevels, that at this point you're just assuming that there's just individual levels that electrons can exist in. So we assume that there's only these certain levels, orbits, that are a fixed distance from the nucleus and has a specific quantized energy. You can't be in between energy levels. You can only be in one energy level, and if you want to go to the next one, you have to absorb energy to jump, to get up. All right, we're going to touch on shielding, and then we'll get back to shielding a whole bunch through this slide, and then through this lecture, and then the next one. But here's what shielding is. Okay, I have, all right, Jake, we're going to use each other here, okay? So shielding is I have an attraction to Jake. Okay, so here we are, direct attraction. And then all of a sudden, Brandon gets in the way. So now Brandon is shielding me from my precious Jake, and I have less attraction to him. That's exactly what shielding is, except it's with electrons. So let's now use this as electrons. Pretend the huge tank of vegetable oil is the protons, right? That's my nucleus. Then I have Jake, then I have Brandon, then I have myself, okay? Who's the furthest from the nucleus? Me. So I require less energy. But I require even less energy, even more or less. I don't even know how to say that, but you get what I mean? Because now I have shielding to my vegetable oil. The protons I can't really see the protons as well because now I have two levels of shielding in front of me. What do electrons do to each other? Are they attracted? No. What do? They repel each other. So even though I'm already at a fixed distance from the nucleus, I have less attraction to it because I'm being repelled by these shielding guys. Does that make sense? So read the shielding effect on your own for a moment. So now we're going to go into first ionization energy, which we write like this. IE1, IE2, IE3. And so forth. So what am I referring to when I say 2 and 3? Ionization energy is the minimum amount of energy that is required to remove the outermost electron, the least tightly held electron, the valence electron, the one that's in the outside shell. So this is IE1. What do you think IE2 is? The second electron, not the second energy level, but just the second electron. So you're plucking one electron out. Clearly that has a certain amount of energy required. Is it going to be greater energy required to pluck the second one, or lower energy? Always greater. Always. So for a same atom, not different atoms, but the same atom, once I remove one electron, it immediately becomes more difficult to remove the second. And then each one's going to be subsequently harder and harder, because not only are you going to have a greater force of attraction with the nucleus, you're going to start dropping energy levels once you start pulling all these valence electrons out, right? So it's going to just start to get harder. So this is a general equation for the removal of an electron, because you now create a positive ion. And this is happening in the gas phase. And you basically can determine the energy required to do this by shining the frequency of light. Frequencies directly related to energy. And then you can calculate the energy required to remove an electron. So it's important to know the definition of ionization energy because you're going to be asked multiple choice questions. Tomorrow I'm going to give you a multiple choice question to try and analyze what the atom is based on the ionization energy data that I'm going to kind of teach you right now. So here's a graph. What should you always do when you get a graph in AP Chem? Read the axes. Excellent. So what does it say? Atomic number. So we're just looking at the periodic table essentially. And the ionization energy is increasing. So we're going to take a look. We have hydrogen has high ionization energy, but helium is the highest amongst all of these, right? So you know this, but maybe you don't. We're gonna kind of go back over the periodic table at this point. So why does helium, down here on the right, why does helium have a higher ionization energy than hydrogen? In other words, it takes more energy to remove its first electron than it does to hydrogen. They have the same shell. They're both in n equals 1, right? Why? Someone must remember. Yeah, I know you're on the right word. It starts with a E. No? Nothing? Do you know why? They're in the same energy level. What's changing for them? I know you know this. Yeah, but what's causing that? Effective nuclear charge, which means what? What's increasing? Okay, you guys don't remember any of it. The number of protons. They're in the same energy level, right? So here I have proton for hydrogen and energy level n equals 1. So this is holding this at a certain force of attraction. But then I have helium with 2 protons holding this energy level. We're not talking about electrons specifically. We're talking about the energy level, how it's holding it. It's going to hold it twice as strong because now it has double the number of protons. So that special word is called effective nuclear charge. So as effective nuclear charge increases, the force of attraction increases. According to Coulomb's law, Q is doubled. Do you understand that? Q is doubled, therefore force of attraction increases. So now it's going to require more energy to remove an electron from helium than it would be from hydrogen. Take a look at the lithium example, the sodium, the potassium. Why are these decreasing? So look at the periodic table. You could always use that periodic table too. This is a new addition this year to my board. I hung it myself. Yep. Sorry, Jillian.
They only have the first energy level, so it's easier to move electrons away.
Well, why is hydrogen higher than lithium though? Go ahead.
Because it only has 1 energy level, but it only has 1 proton.
Yeah, so then what happens to lithium?
It has 2 energy levels, but only 1 proton.
So what's changing according to Coulomb's law? If you don't remember Coulomb's law, look at it. You only have 2 choices, charge or, Jacoby? Distance. So the distance is increasing because you're going down the periodic table, which means you're adding what? Energy levels. So the more levels you add, the further you are from the nucleus, which means distance increases, therefore force of attraction decreases, which is why it's easier to remove an electron from potassium than it is for sodium. Yes? We will get to these little blips here in a minute. You have to be able to explain this. This graph, they love this one. They put it on almost every single exam, which means you know you're going to see it at some point in my class, to be able to explain why. Why is this all happening? Okay? All right, so our general trend for ionization energy is that ionization energy increases as you go from left to right for effective nuclear charge and increases from bottom to top because you decrease the number of energy levels, therefore force of attraction increases. So the highest ionization energy is helium. So sometimes they just ask you a general question, like which of the following atoms has the highest ionization energy, and it's just easy to just memorize the trend. All right, so let's take a look at what we were just discussing, but now it's written down for you. Here are the actual numbers for hydrogen and helium. So helium is pretty much double that, and that's because helium has twice as many protons. So Q is doubled, therefore the force of attraction is doubled, therefore the energy to remove the electron is doubled. We're looking at lithium. Lithium has half the energy, and we already said hydrogen is in energy level 1, lithium is in energy level 2. Since it's further from the nucleus, the energy is decreased. All right, this is just showing you, this is what we expect to see. According to the Bohr model, we expect to see shells. So n equals 1, n equals 2, 3, we expect to see this, okay? That's what ionization data suggests, is that they have shells. We're going to get to why there's subshells in just a little bit. So you already know that there's S and P and D and F, but assume for the moment that you don't, because this is where we're headed, is how did they figure out there was S, P, D, and F? So right now, they just know that there's subshells, and they know from this data, when they go from lithium to neon, and then all of a sudden it drops again, that tells them these must all be in the same period. Do you agree? Because you see like a general trend, and then all of a sudden it drops, and you're like, well, this must now be in a new energy level because the energy decreased dramatically. So we must have added an energy level. So scientists recognize, oh, there must be 8 atoms, 8 electrons essentially, 8 elements in this period. This only had 2, right? So the data suggests that the first row only has 2 electrons, that the second sublevel has 8, the third has 8. But at this point, they're assuming they're all the same. But this little blip causes that problem that they're not all the same, right? If they were all the same, what would you expect to see? A straight line, right? But because there's this little blip here, that means that they're not all the same. They're all in the same period, but they're not identical. So why do you think this blip is here? You can see this is 0.1, 0.2, 0.3. Any ideas yet? I mean, you could look at the periodic table to see why. Anyone? Anyone? Okay. I'll get there for you. Look at it. It's lithium, beryllium, and then boron. What happened? What changed from beryllium to boron? You know this. What happened? You went from where to where? S to P. Does that make sense? Okay, so you have an S sublevel, because you guys know that, and you have a P sublevel. And so, like, the vegetable tank is my protons, and now I have what causing me between P and S? What's that special phrase now? Shielding. So that tells me that these electrons here are shielding this guy. So boron's being shielded by lithium and beryllium, and then it goes up, the pattern follows. But initially, the energy required to remove that electron decreases for a second because the force of attraction just got weaker because there's something shielding it. So this is what it's telling us. Initially, this is what we assumed. You could hold 2, you could hold 8, you could hold 8, but then we recognize that there is shielding. And then this shielding effect and where the electrons are will be tomorrow's lesson when we discuss PES data. So we'll go over specifically how this works, and what we're going to look at tomorrow is how to basically come up with electron configuration from this specific data here, okay? That's it.